Good day guys, my name is Iko from Exclusive Tutorials, and today we'll be treating scalars dimension. So they'll be treating dimensions. They'll be treating dimensions for those for post-UTME class. We'll be treating dimensions and units. Okay, first of all, before we talk about the dimension, we'll have to talk about two major things. We'll have to talk about what are fundamental quantities, and what are derived quantities. Okay, without going too far, fundamental quantities are those quantities that are independent of all other quantities, while derived quantities are those quantities that result from the combination of two or more fundamental quantities. Okay, now let's look at some fundamental quantities. For fundamental quantities, we have mass in kg. We can have length in meter. We can have time in seconds. We can have temperature in Kelvin, and we can have current in ampere, and we can also have quantity of a substance in mole. So these are some of the basic fundamental quantities. Another one is luminous intensity in candela. Okay, after talking about that, next we'll talk about derived quantities. We just said derived quantities are those quantities that result from the combination of two or more fundamental quantities. So talking about derived quantities, we're going to be talking about, okay, let's say for example we have velocity. Now the truth is that derived quantities are a combination of two more fundamental quantities. Now velocity is equals to displacement over time. Now you can see that velocity is a combination of two fundamental quantities, which is displacement, which the unit is length, so that is meter, then time is seconds. So that is a combination of two more fundamental quantities. That is the derived quantities. And there are a whole lot of examples. We have velocity, we can have acceleration, we can have force, we can have pressure, we can have stress. They are countless examples of derived quantities. As long as they are a combination of two or more fundamental quantities, they actually make up a derived quantities. Now we're actually going to be looking at dimensions. Now what is the concept of dimension? The concept of dimension is used to simply represent derived quantities in the way they were actually made up, from the fundamental quantities. Now we'll be looking at three major concepts when looking at dimensions. Now the concepts are: mass is represented as m, time is represented as what? T, length is represented as L. So mass is presented as m, time is presented as T, length is presented as L. Another additional one can be current is represented as what? A. So we're going to be working with these four for now. Okay, now let's look at some very good examples. Now let's say what is the dimension for area? Very simple. You know that normally the area, let's take a square or triangle for instance. The area of a square is length times length. The area of a rectangle is length times breadth. The area of a triangle is 1/2 base times height. Now observe something. Numerical values does not apply to dimensions. So whenever you are making up dimensions, we don't add the numerical values to it. So now let's imagine this was also base times height. Now all these are the same, the fact that they are all lengths. So area is equals to length times length is equals to what? Length square. The same applies to volume. You know that volume is equals to length times base times height, which is equals to length times length, which is equals to L cube. So this is the dimension for area. This is the dimension for what? For volume. Now let's take another example. Now let's take, for example, what is the dimension for velocity? What is the dimension for velocity? Now we know that velocity is equals to displacement over time. Now we know that displacement can be represented in length, so this is equal to length over time. Now to take this t upwards, it will carry the inverse sign, so that will be equals to lt minus 1. Hope we get. So this is the dimension for what? Velocity. Let's take another one. Let's take the dimension for acceleration. Let's take the dimension for acceleration. Now we know that acceleration is equals to velocity over time, and we know that velocity is equals to displacement over time. So acceleration is equals to displacement over time, that is for velocity, then over time again for the time below it. So this is velocity over time. So acceleration is equals to displacement is length, it can be represented in the form of L, then t over t over t. This will give lt minus 1 over t. Now for this t to come up, we'll now have something like lt minus 1 minus 1. That will be equal to lt minus 2. Hope you all get. So acceleration will be lt minus 2. Now let's take the dimension for force. Let's take the dimension for force. Now force is equals to mass times acceleration. Mass and acceleration. And new mass is represented as m, and we have already derived acceleration to be lt minus 2. So mass is equals to mlt minus 2. So that will be for force. Okay, next let's derive the dimension for work. Let's derive the dimension for work. Now work. Now we know that work is equals to force times distance. And we have already derived force. We have already derived force to be mlt minus 2. So this will be distance can be represented in L. So you get distance can be represented in L. So this will be ml squared t minus 2, because L times L is what? L squared. So that will be the dimension for work. So now let's represent the dimension for pressure or stress. Now we know that pressure is equals to force over area. Pressure is equals to force over area. Now this is equals to, we have already derived the dimension for force to be mlt minus 2. Now in case you don't get it, you can go to the previous examples and check for force. Now we know that area, we derived area earlier and first. We know that area is L squared. So this will be equals to ml 1 minus 2. Because of these two, t minus 2. This becomes ml minus 1 t minus 2. So this will be the dimension for what? This will be the dimension for pressure, ml minus 1 t minus 2. Now let's derive the dimension for density. Okay, now we know that density is equals to mass over volume. So this is pretty straightforward and easy. And we know that mass can be represented in the form of m, volume can be represented in the form of L cube. So density is ml minus 3. Very easy. Now next, let's represent the dimension. Let's represent the dimension of, let's see, we're doing 2 at a time. Okay, let's see, we are going to represent the dimension of mass flow rates and volume flow rates. Okay, instead of going the easy way, because mass flow rate is just mass over time, so that would just be t minus 1. Volume flow rate is volume over time, That will be L cube over time. That will be L cube T minus 1. But I want us to actually go through the long way. Now, let's start from volume flow rates. Now, volumetric flow rates or volume flow rates or volume flow rates is equals to area times velocity. Area times velocity. So that will be equals to L squared times LT minus 1. Please, if you don't understand how we got L squared or LT minus 1, you can go to the previous examples. That will be L cube T minus 1 for volume flow rates. Now, to get our mass flow rates, don't forget that mass flow rates is equals to density times volume flow rates. Mass flow rate is equals to density times volume flow rates. So this mass flow rate will be equals to, what is density? Remember we have derived the dimension for density before, and it was ml minus 3. Then volume flow rate, we derived it just now, it was L cube T minus 1. Now this will become ml minus 3 plus 3 T minus 1. This becomes L0 T minus 1. Now remember, n trace power 0 is what? 1. So this will become mt minus 1. So that will be it for the mass flow rates. Now let's take other examples. Now what is this? What is the dimension for strain? Let's say we have something like, what is the dimension for strain? What is the dimension for strain? Now we know that strain is equals to extension over length. Now we know that extension can be presented in length can be presented in length. So strain is dimensionless. So strain is what? Dimensionless. Now let's say we have to represent the dimension for something like Young modulus. Now Young modulus is equals to stress over strain. Now since strain is dimensionless, we can say the dimension for Young modulus is equals to the dimension for stress. Now the dimension for stress is also equals to the dimension for what? Pressure. The dimension for stress is also equals to the dimension for what? Pressure. And I think I've done that before, so you can just go back and view the example. Now let's also take the dimension of other quantities that might be used that are very popular. We have heard of this one before. The dimension for electromotive force. Okay, let's start from a simple concept. What is the dimension for quantity of electricity? Now that Q is equals to IT, and they are both dimensional quantities, fundamental quantities. Current can be presented in A, T can be presented in what? In time. So dimension for Q we can say is what? A what? T. Now, what is the dimension for electromotive force? Now we know that work done is equals to quantity of electricity times what? V. That is the voltage. And we're actually looking for what? The dimension for this what? V. Hope you are getting where we are going. We're looking for the dimension of this V. So we can actually now say, okay, V is equals to W over Q. Now remember the dimension for Q is 80, and we know that work done is equals to what? Force times distance. And we remember the dimension for work done. If you don't remember, you can go back to the previous examples and check the formula for work done. Now we know that the dimension for work done is ml squared T minus 2. Dimension for work done is ml squared T minus 2. That is force times distance. Now the dimension for Q, we already proved it before a while ago to be what? A what? T. So what we have to do is to divide. So that will be ml squared T minus 2 minus 1 will be T minus T A minus 1. A minus 1 because A is what? Coming up. So this will be the dimension for what? Electromotive force. Let's take other dimensions. let's say we're taking the dimension for a quantity like resistance. Okay, what is the dimension for resistance? Okay, we know that resistance can be related with the formula. Resistance can be related with the formula. Resistance can be represented with the formula. V is equals to what? I arrow. Now we already know that resistance here, arrow is equals to what? V over what? I. Now, okay, now let's imagine we forgot how to derive the formula for electromotive force. This is V electromotive force, which we just derived a while ago. Just derived electromotive force a while ago. Now remember that I said electromotive force is W over Q. So this will be over I. So R will be equals to ml square T minus 2 all over AT, then all over A. Remember that this is the current. So now we can clean this so that we can represent what we have on top. So remember that then R will now be equals to, let's represent this one first. That will now be M L square T minus 3 A what minus 1 all over what A. So dimension for resistance is ML square T minus 3 A minus 1 will go up minus 2. So this is the dimension for what? For resistance. This is the dimension for resistance. Now let's take another one. Now let's say they ask us for the dimension of resistivity. We can represent resistance and resistivity with the formula. R is equals to resistivity times length over area. Now we can just say that resistivity is equals to resistance times area over length. Now we can say resistivity is equals to, we can bring this ml square T minus 3 A minus 2 times L square all over what? This can cancel what? This. So we can say dimension for resistivity is equals to ml square T minus 3, sorry, ml3, because if this cancels this leaves one L here. So L times L square will give us L3. So T minus 3, then A minus 2. So this will be the dimension for what? Resistivity. Now let's say they asked us for the dimension of conductivity. Let's say they ask us for the dimension of conductivity. Let's say they said, what is the dimension for conductivity? Now we know that conductivity is equals to 1 over resistivity. Now since we already know our resistivity here, so all we have to do is 1 over ml cubed T minus 3 A minus 2. Now this will be m minus 1 L cubed L minus 3, because 3 is coming up to guide the negative sign. Now when this minus comes up, it turns to 3, then A2. This will be the dimension for what? Conductivity. This will be the dimension for conductivity. Now what other quantity can we prove the dimension? Okay, let's prove the dimension for the universal gravitational constant, G. Now we know that force relates with universal gravitational constant to this formula. Force is equals to G m1 m2 over r square, where r is radius, or it can also be in length. So therefore we know that, let's use small letter r. Therefore we know that G here is equals to force times r square over m1 m2. These are masses. This is force, this is radius. Now we know that G is equals to force. We have put force before to be mlt minus 2 times radius square. Simply means L square, because radius is length, so L square. Then we know that this mass is m1 and m2. This mass is m1 and m2 are masses, so we can say m times m. Now this m can cancel one m here because they are all joined by multiplication sign. This will multiply this, so that will be g will be equals to L cube t minus 2 over what m. Now this can go up to be, this m will come up, L minus 1 L cube t what minus 2. So that will be that for gravitational constant. Now let's take for our gas constant R. Our gas constant R from the formula PV is equals to nRT. We're looking for the dimension from R. Now we know that R is equals to P is pressure, this is volume, all over this is mole, then this is what temperature. Now we know that pressure is equals to force over area. So the dimension of pressure is ml what ml minus 1 t minus 2. So if you don't understand how we solve this thing, you can go back to our former video and check out how we solved it. Now therefore R will be equals to ml minus 1 t minus 2 times volume is L cube, mole can be represented in mol, temperature can be represented in what Kelvin. Please don't forget this. Now this can multiply this, so it will be m minus 1 plus 3 ml square t minus 2 over mole times Kelvin. So this will ultimately give us ml square t minus 2 mole inverse K inverse. Okay, for those that can't see it, let me write it well. So that will be ml square t minus 2 mole inverse K words inverse. So that will be for universal gravitational constant. Okay, let's take the dimension for coefficient of expansivity. You know that it can be represented by the formula alpha equals to, or let's say linear expansivity, linear expansivity, alpha is equals to change in length over original length into change in temperature. Now you know that length can be represented in m, sorry, length can be represented in L, while temperature can be represented in Kelvin. So it will be equals to L over L times K. This ultimately cancels this, so this will be equals to K watts inverse. So that was just the dimension for the coefficient of linear expansivity. Now this is also the for area expansivity or superficial expansivity. It will still apply, because remember that superficial expansivity is equals to that will be 2 alpha. So numerical value does not apply to dimension, so it will have the same dimension as what K inverse. So let's look at some application of dimension. Now one of the major application of dimension is to test the validity of an equation. Let's say we have an equation, a very popular equation, v is equals to u plus at. We can use the concept of dimension to prove that this equation is correct. Now we know that the dimension for volume is Lt minus 1. Sorry, velocity. The dimension for velocity here is also Lt minus 1. Dimension for area is Lt minus 2. Then this time is t. So we can work on this one. We can say Lt minus 1 is equal to Lt minus 1 plus t minus 2 times t will ultimately give us Lt minus 1. So Lt minus 1 is equal to 2Lt minus 1. Now remember I said numerical value does not apply to dimension. So we can also say that this is equal to what this, because numerical value does not apply to what dimension. Okay, now let's test the validity of another equation. Let's test the validity of another equation. Let's say we have an equation like S is equal to ut plus S is equal to ut plus 1 over 2 at cube. So when our s is in what? Distance, so that is m. Velocity is lt minus 1. Sorry, distance is in l. Velocity is lt minus 1 times t plus 1 over 2. Acceleration is lt minus 2 times t cube. So this will give us l is equals to this minus 1 plus 1 is 0. So this will leave us with l plus 1 over 2 minus 2 plus 3 is 1 LT. So we can see that this equation is not dimensionally correct because the left hand side is not equal to the what? The right hand side. The left hand side of the equation is not equal to the what? The right hand side of the equation. Okay, now let's test our equation. Or let's say if the equation was the normal one, like s is equal to ut plus 1 over 2 at square. This is the normal one. So l is equal to lt minus 1 times t plus 1 over 2 times lt minus 2 times t square. So this will give us l is equal to l plus 1 over 2l. And remember I said that numerical value does not apply to dimension. So we can see l is equal to the left hand side is equal to the what? The right hand side of the what? Equation. Okay. Now let's prove if this equation is correct. S is equal to Vt minus 1 over 2 At square. S is equal to Vt minus 1 over 2 At square. You guys should try it. By pausing this video and trying it. Then know that S is equal to Lt minus 1 times T minus 1 over 2 times Lt minus 2 plus Lt minus 2 times T square. So you can say S is equal to L minus 1 over 2 L. So you can also say this equation is dimensionally correct also. This equation is what? Dimensionally correct. So now let's look at some other complex exercises under dimension. Look at some other complex exercises under dimension. Okay, let's say we are faced with a question like this. If the dimension for, let's say we have something like, if dimension for universal gravitational constant, the dimension for universal gravitational constant is given by mn t ml t p l z. Find n plus p minus z. Let's see if we are given this kind of question. Okay, now you need to solve this kind of question is to first look for the dimension of what was stated in the question. Now what was stated in the question was the universal gravitational constant. That was what was stated in the question. Now you know that universal gravitational constant is equals to force times r squared over m times m. I believe we initially proved this. So this will be equals to mlt minus 2 times l squared all over m squared. One can cancel one here. So this will be m minus 1 l cubed t minus 2. So once you have gotten this m minus 1 l cubed t minus 2, we cannot equate this to what they give us here. So we cannot say m raised to the power n, t raised to the power p, l raised to the power z is equals to m minus 1 l cubed t minus 2. So we can now see now that you can say n is equals to minus 1, p is equals to minus 2, p is equals to minus 2, while z, which is for L, z is equals to what? 3. Now, once we have gotten this, we can find the output to find n plus p minus z. Now, what is n plus p? N plus p, that will be minus 1 plus minus 2, then minus z. Minus z is minus 3. So that will be equals to minus 1 minus 2 is what? Minus 3. Minus 3 minus 3 is what? Minus 6. So this will be it for dimensions. In case you have any other questions, feel free to ask them in the comment section. I remain Dr. Iko, and that is for school tutorial. Please remember to subscribe. Thank you.